Hi guys, we're going to look at exponential functions with function bases. So we've had a base of e, we've had a base that has a positive number, and now we have a base that is a function. So if we look at this first one, my base is x. X is a function. So if I look at this second example right here, my base is sine of x. That's also a function. When we have a function raised to a function power, we're going to use the natural log to differentiate. So first step on this first example, we're going to take the natural log of both sides. So natural log of y equals the natural log of x to the power of x. Now with power rules, we can say that this is also equal to the natural log of y equal to x times the natural log of x, because we can bring that power in front using our natural log power rule. From here, I have natural log differentiation, and that's pretty simple. So we're going to take the derivative of both sides. So I'm going to show my work. So I'm going to say I'm going to take the derivative of all of this stuff right here. Now, the derivative of the natural log of y is 1 over y dy dx equal to, this is a product rule right here, so we're going to take the derivative of x, that's 1, and then leave natural log of x alone. Then add x, leave it alone, natural log of x. The derivative of that is 1 over x. Now, I know that x divided by x is just 1, so I can simplify this a little bit and say this is the same as 1 over y dy dx equal to the natural log of x plus 1. Now the goal was to get dy dx, so we just need to get rid of that y. So we're going to multiply to the other side. Dy dx is now equal to y times all of that, natural log of x plus 1. Because I know what y is equal to, and I want to have this derivative in terms of x, I'm just going to substitute what y is equal to, and that's x to the power of x. So one more step, we can say that dy dx is equal to x to the power of x times the natural log of x plus 1. So that's using your natural log to help you differentiate. So let's look at another example. Find the equation of the line tangent to y equals sine of x to the power of cosine x at the point pi over 2. So first off, I'm just going to know that I need both the slope and a point to write the equation of a tangent line. So since I'm already thinking about it, I'm going to go ahead and do my y value. Since my x value is at pi over 2, my y value, I find that by saying y equals sine of pi over 2 to the power of cosine pi over 2. So sine at pi over 2 is just 1. Cosine at pi over 2 is 0. So 1 to the power of 0, that's just 1. So now I have my x and my y for my tangent line. Now I need my m, my slope. And we know that finding the slope just means we take the derivative. So we are going to use our natural log to help us out with this derivative right here. So we're going to go the natural log of y is equal to the natural log of sine x to the power of cosine x. And just like we did before, we're going to use the power rule for natural logs and say that this is the same as cosine x times the natural log of sine x. And now we can differentiate. So we're going to take the derivative of all of this right here. Derivative of this one, we just did that. That's 1 over y dy dx. We did that in the previous example. Here we've got a product rule again. So derivative of cosine is negative sine. So we have negative sine x times, we're going to leave this one alone, natural log of sine x, plus, I'm going to have to write underneath because I wrote too big. Leave the first one alone, that's cosine x. And then the derivative of the natural log of sine x. Remember, this is 1 over whatever we're taking the natural log of times the derivative of that function inside. It's like a chain rule there. So times cosine x. Now I can probably pretty this up just a little bit right here, not by a whole lot, but this is 1 over y dy dx is equal to, I would say, cosine times cosine, that's cosine squared. Right here I'm not going to be able to do much, so I'm going to go negative sine x times natural log of sine x, plus we have cosine squared x over sine x. And that's about as pretty as I'm going to get that. So now to get the dy dx by itself, I'm going to say y dy dx equals y times all of that right there. So negative sine x, natural log sine x plus cosine squared x over sine x. Now, we can substitute that back in right here, or we could leave it as y, because we already know the y value. It doesn't really matter to me. We can say that y is equal to sine x to the power of cosine x, but I also have my y value already, so it doesn't really matter. So I'm going to go ahead and leave it the way it is, and I'm going to say the derivative at pi over 2, well, we know that y is 1, because we solved that at the beginning. We're just going to sub in 1 for y times negative sine pi over 2, the natural log of sine of pi over 2, plus cosine squared at pi over 2, and sine at pi over 2. We talked about these values just a second ago. Sine at pi over 2 is 1, so we have negative 1 right there. Okay, the natural log of the sine of pi over 2, well, we know that sine of pi over 2 is 1, so we have the natural log of 1. And then here, cosine pi over 2, that's 0, so we have 0 squared on top. And then sine pi over 2, that's 1 right there. And this is all times 1. That's not really going to make any difference, so I'm going to stop writing that 1 in just a second. Now, natural log of 1, that's 0. So we have negative 1 times 0, well, that's 0, plus 0, because 0 divided by 1 is just 0. So our slope is 0. Now, to write the equation of that tangent line, I'm going to come over here because I have run out of room. Tangent y minus 1, that's our y value that we found at the very beginning, equals m, that's 0, times x minus pi over 2. Now, you might also remember that a slope of 0 is that horizontal line. It's only the y value, so you could also write it as just y equals 1.